Okay, good afternoon. Welcome to the environmental lecture presented by the environmental group of the American Chemical Society Pittsburgh local section. I'm your host, Ron Honglin, and chair of the environmental group. The environmental All right. So the environment group is a topical group within the local section. We support various activities, including this environmental lecture series, which we intend to continue monthly with speakers who are experts and leaders in their field to promote a deeper understanding of science, technology, and environment. And our next lecture will be on May 1st at 12 p.m., featuring Professor Rito Geary from University of Pennsylvania. He will be discussing higher abrasion particles in the environment. And I just want to let you know that this lecture is being recorded and will be available online. Later, I'd like to remind everyone that the views and opinion expressed in this and any future lectures are solely those of presenters and does not necessarily represent the views of the American Chemical Society Pittsburgh local section. And now, it's my great pleasure to introduce today's speaker, Dr. Kenneth Barker, Professor of Chemistry and Biochemistry from the University of Texas at Dallas. Dr. Barker graduated from WPI in 1982 with a BS degree in chemistry. He then earned a PhD degree in inorganic chemistry from the University of Florida in 1986. And after a postdoctoral appointment at the University of Pennsylvania, Dr. Barker joined the faculty at the University of Texas at Dallas. Most recently, he completed a term as head of the Department of Chemistry and Biochemistry. He has also served as editor for 2 journals. Dr. Barker has been recognized with numerous awards, including an National Science Foundation Presidential Young Investigator Award. He was also named a fellow of the American Chemical Society in 2011 again. Dr. Barker has published more than 350 peer-reviewed papers and book chapters and received numerous citations. Dr. Barker is not only a professor and educator, but also an inventor and entrepreneur. He is a co-inventor on 45 patents issued and pending, many of which have been licensed, and co-founder of DB Therapeutics, a company developing cancer therapies based on invention in his lab. His research has focused on porous materials with applications in areas such as catalysis, membranes, energy storage, and drug delivery. And today, Dr. Barker will talk about metal organic frameworks or MOF materials and the potential application in PFAS destruction. And with that, please join me and welcome Dr. Kenneth Barker. And thank you everyone for joining us today. And I hope you enjoy the lecture. Dr. Barker, the floor is yours. You can take over now.
All right. So
let me stop sharing.
Yeah.
All right.
All right, so all right, can you see my screen?
Yes, good,
How about that?
good.
All right. So thank you for the kind invitation to tell you what we've been working on. And I know as an environmental group, you probably want to hear more about the PFAS than the metal organic frameworks. But as my advisor used to say, he said it's more important that you tell a good story. So to get to the PFAS, I have to tell you a story. And this starts with our metal organic frameworks. So before we get started, we were just having a quick chat about the solar eclipse. This is actually what it looked like in Dallas. It was pretty impressive. And I guess for some of you in Pennsylvania, you got to see the same show. Just to tell you a little bit about UTD, we're a university of about 30,000 students, not actually located in Dallas, but we are right on the edge of Dallas County. So I guess that counts. And this is a shot of the campus. And of course, our mascot is we're the Comets. So everybody was excited for the solar eclipse because of our our mascot, of course, is we call him T-Mock, which is Comet in reverse. So, at any rate, uh, so just to give you a little background here, I've been interested in porous materials for almost 40 years now. And we originally were working on zeolite type materials, making new zeolite materials. That evolved into some mesoporous materials. And then, of course, the mesoporous materials are, if you look at the IUPAC definition, are the 2 to 50 nanometers, where anything below that is a microporous. And then we've also looked at carbons, like this is a carbon here. And then we've looked at the hybrid type frameworks. And even though this is a zeolite type structure, it's actually a metal organic framework. So when we became interested in metal, let me just tell you a little bit about what a metal organic framework is, since we have a general audience here. These are basically coordination polymers, and coordination polymers have been around for a very long time. But it wasn't until like 1999 that Omar Yargi and Kitagawa as well reported some of these coordination polymers had very high surface areas, i.e. porosity. And that was a big discovery at the time. In fact, these guys are often suggested that they will get the Nobel Prize. Hasn't happened yet, but it's still possible because this field has really exploded. And so what you have in a metal organic framework is you have a metal or metal clusters, and then these metal clusters are linked together by bridging ligands. So in this case here, you have a basically terephthalic acid, and then you have a tetranuclear zinc oxide cluster that's bridged together. So what's interesting about this is, if you compare it to zeolites, and we did zeolite synthesis for many, many years, it's very difficult to make new structures. Whereas in the case of metal organic frameworks, you almost have an infinite number of ligands that one can use. And then you get almost the periodic table of metals and metal clusters that one could use. And so there's all kinds of new structures being made and reported every day. So some of the applications that have evolved for these materials and things that we've been involved in, everything from membranes, obviously separations is something that involves from the other porous materials like the zeolites, chemical sensors, drug delivery. We've gotten into energy storage, gas storage, catalysis, and that's just to name a few. And there's quite a few other applications that people are exploring for these materials. So there's a lot of interest. Now, one of our entry points into this field, okay, was looking at the rare earth metal oxides. And in this particular case here, I've highlighted the lanthanides, which most people probably couldn't list for you. But we were particularly interested in holmium, okay, HO, holmium. So part of the reason why we're interested in the rare earths and holmium in particular, back in the 90s, we were interested in MRI contrast agents. And then more recently, we've gotten interested in radiotherapy using holmium. And the reason why holmium is because it can be neutron activated and it becomes a beta emitter and also some gamma, so that can be imaged as well. It has a very short half-life, about a day, which means that you can use holmium in radiotherapy, and then after a week or so, you could put it in the trash can because it'll be completely cold. And so what happens in radiotherapy is that you generate free radicals, and of course the free radicals then do DNA damage, and that's how you end up killing the cancer cells. And so we've used some holmium-based oxides. We've incorporated them into bandages, and we use them for the treatment of skin cancer, and that's the company that we started here. So you can see this little bandage here that one then uses for skin cancer. Now, metal organic frameworks became interesting because we could use metal organic frameworks to bind radiosensitizers. And a good example of a radiosensitizer is nitric oxide. And so here's an example of a metal organic framework that we reported where you have this linker, and then you have these NH groups that will react with NO and form what we call a diazonium dialate. And then this can reversibly bind and release the nitric oxide. And so from the radiotherapy standpoint, that nitric oxide can be used to enhance the effect of the holmium. And what that means then is that you don't have to have as much radioactivity in your material if you have a radiosensitizer. I also want to point out that my PhD advisor, Russ Drago, first reported diazonium dialates back in 1959, which I only discovered after he had passed away. And it's unfortunate that I didn't get a chance to chat with him about some of this chemistry that we're actually doing now. So you never know. If we have any students here, you never know what you're going to revisit at some point in your career. So we're interested now in these metal organic frameworks. And again, holmium was our primary rare earth oxide, but not just the holmium. We've gone across the periodic table looking at different metal lines. And so where to start? And that's where now Dr. Juan Vizuet is doing a postdoc in Chicago. He says, okay, well, I am going to start with a very basic linker, one of the first ones that Omar Yagi reported, which was this bis dicarboxylate. We use BDC, terephthalic acid, if you will, and it forms a variety of different metal organic frameworks. And here's an example here where you have a zirconium hexanuclear cluster that's bridged together by these linkers. So we said, well, okay, let's see if we can't use holmium and see if we can't make a stable metal organic framework. Now, one of the reasons why he picked this is because this particular MOF is very thermally stable. And so when you neutron activate holmium, the reactor heats up. It could be 150 degrees or more. And so you have to have a metal organic framework that will withstand those temperatures. And of course, you'd like to have as much metal in there as possible. And you'd like to be porous, or the ability to functionalize these materials for those radio sensitizers. So anyway, so Juan started doing syntheses, and he made, I don't know, 20 new structures. And oddly enough, they were all about the same. They had these dimeric building groups. We use different ligands, we use different solvents, you get different coordinations. And this is one of the interesting thing about the rare earth ions, is they have very high coordination numbers. You work with transition metals, you're used to maybe a octahedral metal complex. Well, here you can have 8 coordinate, 9 coordinate, 10 coordinate, 11 coordinate, maybe even 12 coordinate. And so you get some very diverse structures that form with these. Unfortunately, none of these were terribly interesting. Many of them were just dense frameworks. They had little or no porosity, and they all had these dimeric structures. So Juan says, well, some other work we were doing in the lab, we were making rare earth clusters. Okay, and he says, well, maybe we can make a bigger rare earth cluster, and that might force bigger pores and be able to then functionalize it. And this was based on the fact that we were using some of our carbons to remove rare earth ions from coal ash. And part of the reason why these were so selective is, depending upon the pH, one gets different cluster sizes. So we thought, gee, maybe if we can control that, then we can do, we can make bigger pore structures. And so Juan went to the literature and found that people indeed had made some bigger clusters of rare earth ions, and they used a modulator. Now, what a modulator is an additive that you would incorporate into the synthesis that would weakly bind to your metal and then allow the cluster to form. And it would control basically the crystallization. And so the molecule that was most frequently used and first reported by Dowdy and coworkers was this 2-fluorobenzoic acid. Okay, so he's added some 2-fluorobenzoic acid to his syntheses that he had been doing that were consistently making these dimeric structures, and first synthesis made this beautiful structure, isostructural with UiO 66. And we got this structure back, and the crystallographer said to us, he said, beautiful structure. He said he got these nice fluoro bridges. Wait a minute. I mean, what do you mean fluoro bridges? Where did the fluorine come from? Well, the only place the fluorine could have come from was this modulator, this 2-fluorobenzoic acid. And then the first question you ask, is it really fluorine? Because if you think about where oxygen and fluorine are in the periodic table, crystallography, it's very difficult to prove that it's oxygen or it's fluorine. Now, fluorine fits better in terms of refining the structure, but it's not really proof. So we needed to have some other evidence that we were making fluoro bridge clusters. And for us, really, the best technique that we found was X-ray photoelectron spectroscopy. And so if you look at just the fluorine in these structures, and I should point out that if you look at the starting material, this is a 2-fluorobenzoic acid. It has a binding energy at 686.7. This is the 2,6-difluorobenzoic acid. And then, just as a jumping ahead a little bit here, here's the perfluorohexanoic acid, PFAS, and that's at 689. So what you see is all these organofluorine compounds, they're all roughly about in the same place, okay? Roughly about between 687, 689 electron volts. So then if you look at the metal organic framework, say, okay, well, and this one actually happens to be yttrium, but holmium is the same thing. You see that the binding energy is at 684.7, quite a bit lower than the organofluorine compound. And in fact, if you look at just the metal fluoride, you see that it's at 685. So typically we'll see that for the metal fluorine bonds, it's 683 to roughly 686, whereas the organofluorines, 687 all the way up to 690 is what we've observed. So you can easily tell the difference of when you get a metal fluorine bond, whether you have organofluorine. So that kind of ruled out the fact that maybe we're encapsulating or absorbing the organofluorine compound, because there's no evidence of that. But we definitely have metal fluorine bonds. And this one here on the far right here just shows you the fact that you can resolve these two peaks very easily and see the difference between organofluorine versus metal fluorine. Okay. Also, you could go the other way and say, well, if it's not fluorine, it would have to be an oxygen bridge. And in fact, if you use zirconium, what you get is clearly an oxygen bridge. And so that zirconium, oxygen, zirconium, in the top right here, the green peak, that binding energy is for the oxygen bridges in the cluster. So then if you go over to the metal organic framework, there is no binding energy, there's no peak for an oxygen bridge, okay? And this is just this is a trinuclear cluster with a different linker, and same thing. We don't see any evidence for oxygen bridges. So early on, the first structures we made, there was only fluorine in the framework. So now, one thing I should point out is that the linker, while it is important with regards to the overall structure that you end up with, is not required, of course, to remove the fluorine from the organo, whether it's PFAS or fluorobenzoic acid. In fact, if you just take holmium ions, holmium nitrate, and you boil it up in DMF with your PFAS, you make holmium fluoride. Okay, and that's very easy to see by X-ray diffraction. So one of the things that we discovered was that this was very solvent dependent. So you could have water around, but you needed a solvent like DMF. So DMF, DEF, DMAC, pyridine, all these solvents here seem to work. And one of the problems with something like DMS is I call it a very dirty solvent. In other words, it breaks down very easily, and you'll have a mixture of not only DMF, but also dimethylamine, and you can end up with formic acid in your solution as well. And there's even been reports that you can end up with free radicals in your solution as well. Okay. We think that this is important. In fact, if we add a DMA scavenger to clean up the solvent, remove any DMA or formic acid, there's no reaction. So that's kind of important for this reaction. The presence of water seems to be okay, but it needs to be acidic. If we just throw in sodium fluoride or ammonium fluoride, we don't make these metal organic frameworks. It doesn't work. Now, just to show you an example here too, when we do this reaction in DMAC, which is what the dimethylacetamide, which is what Juan first did. So this is the structure he first made. He got this UIO66 structure, hexanuclear cluster, but when he did the reaction in DMF, he made this structure, which has formate and you can't see the formate in this particular view. Apologize for that. It's going into the plane of the board, but they're now bridging formates into the structure. And of course, this formate comes from the DMF and the still the hexanuclear clusters. So we think that the DMA is important. And one of the reasons we do think that is because if we look at after just a reaction of 2-fluorobenzoic acid with a rare earth ion, and we look at the mass spec, we'll see species where it looks like dimethylamine now is bound to where the fluorine was. Okay. And by the way, we see no evidence of benzene as an intermediate or free radicals, though it's tough to use free radical traps in the presence of rare earth ions because the rare earth ions usually react with the free radical traps. So, but at any rate, we think that the metal is also binding with the carboxylate. We see these kind of species in the mass spec, although that's tough to do too because we got to do this in DMF and they don't like DMF in the mass spec. So, but at any rate, that's a different story. So we think that the DMA, or at least in the case of DMF, is important for this reaction. Now, one of the things that we did was, well, let's do this in water with no DMF. And by the way, bipyridine, much like the 2-fluorobenzoic acid, is also considered a modulator, binds weakly to metals, and you'll end up with a possibly clusters, or you'll possibly end up with bigger crystals, whatever the case may be. And then what in this particular case here, this is with gadolinium. Not surprisingly, we made a dimer. But interestingly enough, in just water with no DMF, you end up with the carboxylates of 2-FBA binding to this dimer. And so we kind of look at this example here in water as a model for maybe a transition step where the organofluorine compound first has to bind to the metal ion and before it can extract off the fluorine. And in fact, if you take this cluster now, this dimer with 2-FBA bound, and you heat it up in DMF, it forms this structure. Okay. And in this particular case here, this linker you end up with, and you have this linker, which is has 3 carboxylates on it. And I should point out, this is interesting how we got into the PFAS. A lot of people are looking for ways to absorb the PFAS. And I said to Simon, in the upper right-hand corner here, I said, see if any of our MOFs, our metal organic frameworks, will absorb PFAS. And she kind of misunderstood me. She thought I meant do the synthesis with PFAS. And sure enough, she did the synthesis instead of just trying to absorb it. And she made this structure. And these are not hexaclusters, but nanoclusters. So you got 9 metal ions in this structure, and there's also a trinuclear cluster as part of this overall structure. Now, interesting enough, if you try to use the 2-fluorobenzoic acid for this reaction, it doesn't really work. But this PFAS works like a charm, and it, in fact, is better at, and I should point out too, that this mononuclear cluster now with a tricluster, these are neutral frameworks. And if you made the oxo version of this without any fluorine, it's a charge framework. And there's a big difference. You can actually find the DMA molecules in the pores, and and so we have a neutral structure. Also interesting with this particular one here is that if you look at the XPS, this is the oxygen XPS, you'll actually see a little bit, this tiny peak here of some oxo bridged. And so this was the first time we actually said, okay, well, you can actually get a little bit of oxo or hydroxo bridged clusters in there. It's mostly fluoro bridged, but you can get a little bit of oxygen bridged. And if you actually add peroxide to the synthesis, you can drive it to mostly the oxo bridged. And this is, since we first reported some of this chemistry 2 years ago, now people have reported a number of structures where they'll see a mixture of fluorine and a mixture of oxygen. Okay. And one of the points that always comes up is, what difference does the fluorine in the framework make? And here's just a very simple one here where it's actually a little more stable. So the red one is the oxo bridge, and the blue one is the fluoro bridged. And you can see that thermally it's a little bit more stable having the fluoro bridged structure. Okay. And I should also point out that we've made, using these PFAS molecules like the perfluorohexanoic acid, we've made a number of different MOFs, and here's another one here. This is actually kind of an interesting story because, again, you get a crystal structure and you say, where did this come from? Because when the student brought me the structure, she said, well, I have a persulfate bridge in this structure. And I'm like, where did that come from? And it turns out there's sulfate in their DI water, because she's using DI water. So obviously, I said, you use tap water? He said, no, I use DI water. And of course, you take the DI water and you run it to the ICP, and of course, you see the sulfur in there. And what happens is some of these ion exchange resins, when they start to break down, the pH changes. You get some of these other species that show up in your water, and they can actually end up in some of these structures. And this is one of those weird cases where you end up with this structure. And again, this is a perfluorohexanoic acid cluster that's bridged by persulfate. And you can show that it's definitely persulfate. This is the old iodide test where you mix it and it forms iodine, turns brown. It's also antibacterial. And, here's just an example here. This is an E. coli. And you can see after 3 hours, it's just about all the bacteria are destroyed. So, a lesson to take there is that you never know what is going to come up with some of these structures, and sometimes impurities end up giving you something interesting. And of course, if you go back now and you add persulfate to the synthesis, you can easily make this structure. But first time she made it, it came from our water. So here's just kind of a little bit of a summary of the type of clusters that we've made. Trinuclear clusters, a couple of different types, hexanuclear clusters, mononuclear clusters. It's kind of interesting that it's 3, 6, 9. So you'd say, well, is there now going to be 12? In other words, are we forming a trinuclear cluster first, and then it assembles to form hexa and nona? Who knows? But it is curious that you form these multiples of 3. And since we first reported the first fluoro bridge structure, these are some of the linkers that other people have now made into fluoro bridge MOFs. And the different linkers will make different clusters, as you see here, and some are selective for the tri and nona cluster. And so one of the questions you'd ask is why? And we think that there's a balance between the pKa of your linker and the pKa of your organofluorine compound. And if you take something like the hexafluoro hexanoic acid, that's pKa is actually slightly negative. So it's actually pretty acidic. And so now you're competing with some of these linkers for these different structures, and that must be what's driving formation of some of these different clusters. So anyway, just let's get into some of our PFAS chemistry now. And for those, our environmental group here, I'm sure you're well familiar with this, but let's just talk a little bit about PFAS themselves. It's interesting that these PFAS molecules, mostly looking at the hexanoic acid, but we also looked at the octanoic acid. We looked at the sulfate, which also appears to work. a variety of different aromatic organofluorines that work as well. But these PFAS molecules are by far the best in terms of giving up their fluorine. So one thing we know is that we can take a rare earth ion, boil it up in DMF with a PFAS, and we'll end up making metal fluoride. And the metal fluorides are usually are pretty insoluble, so they just precipitate out of solution. And you have a whole range of metals that work for this. The heavier metals seem to work a little bit better, although we can get cerium to work as well as yttrium and scandium and things like that. And each metal is a little bit different in terms of how well it works, but they all seem to work to some extent. So when we started looking at possibly using this chemistry for bioremediation of contaminated water, contaminated soil, things like that, it was interesting to see what the actual concentrations were out in the environment, and then of course what the limits are. And it's really a tiny amount that's out there. And if you think about parts per trillion, we're talking about what the we're recommended limits are, and then try to put that in perspective. A trillion gallons is huge, right? So you want to get the amount of PFAS in a trillion gallons down to a nano nothing, right? And so what that means is you're certainly not going to be treating a body of water like that. And I should have pointed out too, when we talk about soil, this is from the internet here, just showing you the Dallas area, where we have a number of contamination sites. In particular, one that's gotten a lot of press is there's a Navy base now closed because of PFAS. And for years now, they've been trying to, remove soil, and because they want to repurpose the base for housing and other, types of development, but they can't do anything with it yet because it's still contaminated. And so they've slowly been trying to remediate that site. But just to give you some perspective on, the size of the scope of this problem over around the country. And so obviously the red dots are the worst. The blue, not as bad, but this just gives you this is nanograms per liter, but gives you an idea of what we're dealing with. So we also then delved into, well, what are the people doing? So if we want to concentrate this, then we have to use an adsorbent. And people have used metal organic frameworks as adsorbents, I should point that out. But that would be a fairly expensive adsorbent. Carbon is probably the cheapest one, and most carbons will do a pretty good job at absorbing PFAS, although people have looked at membranes, they've looked at ion exchange resins, and these all are fairly effective. But then once you've absorbed it, you have to deal with it because it's not going away. And you certainly don't want to start putting this stuff in landfills. So you now have to do something to destroy those PFAS. Now, the simplest one is incineration, where you burn it, right? But the problem with that, of course, it's obviously, forget about the fact that it's energy intensive. You could end up with fluorine in the atmosphere, whether it's HF, or whatever else, other products you could have. And so that's not the most, and it's expensive too. So it's not the best approach to this. Supercritical water got a lot of press a number of years ago. Again, very high pressure to get to supercritical water. It's effective, but again, it would be fairly expensive. And the question is really how much could you treat? Plasma discharge, electrochemistry, these are all effective as well. But again, are these practical in terms of treating adsorbed PFAS? One reaction I'll talk about that again has gotten a lot of press is a DMSO, and but you also produce HF, and a lot of people don't know that DMSO can actually be explosive, at certain temperatures and pressures. So that's kind of a downside to that. But at any rate, and finally, photocatalysis, that's another possibility as well. In fact, I have a colleague who's looking at photocatalysis, and this can be effective. This is a MOF on the right. This was reported by Hongkai Zhao at Texas A&M. And these are effective. But again, part of the challenge is, we're going to use we've done some photocatalysis as well. You have to have something that you'd like to absorb in the visible range. Things like TiO2 are very effective. You generate hydroxyl radicals, and these are effective oxidants, but something like TiO2 with a wide band gap only absorbs a few percent of the solar spectrum, so not very effective. Interestingly enough, and we've done some work with doped cerium oxide, that moves into the visible region, so you get much higher absorption. So, at any rate, here's the challenge. What it comes down to is the bond energies for the CF bond, and this is, of course, why these are forever chemicals, is because they're so strong. And if you look at just hexanoic acid, you can see that they're all well above 107 kcals. So one of the questions that you would ask is, when you have something like hexanoic acid or perfluorohexanoic acid, what fluorines are actually removed? So what we think is, and again, we don't know for sure because we don't have model compounds. We think for sure the fluorines adjacent to the carboxylate come off. And that's consistent with what we observed with 2,4-benzoic acid. I should have pointed out, if you use the benzoic acid with fluoride in the para position, it doesn't remove the fluoride. So that tells you the proximity to the metal seems to be important as well. And we've already pointed out that we think solvent is critical here. We seem to have some NMR evidence of having, again, dimethylamine bound to the acid. Now, what we do is we'll do a reaction and we'll take the fluorine NMR. And we don't have model compounds. So we try to model the NMR to see what we have. And again, it seems like mostly the fluorine's at this position, and then some of these other ones seem to be in lesser amounts, but they're removed as well. Okay. Do we remove all the fluorines? I don't think so. And I don't know whether it's breaking down. But in talking with people working in this area, they seem to think if you just remove a few of the fluorines, then it really becomes biodegradable at that point. I don't know. But at any rate, so that's where we're at. And so again, trying to develop a system, again, we're going to rely on the fact that we can take a rare earth ion, and in this case, we're using yttrium. One of the questions you'd ask is, well, isn't this going to be an expensive process? Well, you take something like yttrium, or cerium for that matter, and they cost about the same as copper. They're actually surprisingly abundant and not that expensive. Now, holmium, that's a little different story. That's, and some of these other ones, you've probably heard discussions about how dependent we are on China for some of these rare earth elements that go into batteries and electric vehicles, and all that's true. But an element like yttrium is fairly abundant. But at any rate, so we make the metal fluoride, and again, by XPS, you can show that you readily make the metal fluoride. And again, if you want to just compare it to the starting perfluorohexanoic acid, you can easily tell the difference between the organofluorine compound and the metal fluoride. So we know that chemistry works very well. And of course, you can also verify that by X-ray diffraction too, in addition to the XPS. Okay. So now what we did was, let's see if we can't put together a system here where we take the PFAS, in this case, we're again looking at the perfluorohexanoic acid, and we're going to adsorb it. And we've looked at a lot of different adsorbents, carbons. We've got a whole bunch of different carbons that are effective, ion exchange resins, layered double hydroxides. I'll mention that. That actually works fairly well as in terms of absorbing the PFAS. So then what we do is once it's absorbed, then we take the rare earth ions, like yttrium, for example, and we take this carbon, we heat it up in DMF with the rare earth ions, and you can easily show that you make the metal fluoride. Okay, and the metal fluoride is you clearly see it by XPS, and of course you can see it by XRD. So now, to get a complete system here, now we have to take this metal fluoride and we have to regenerate our yttrium ions. So all you got to do is take the carbon now that has the metal fluoride on it and heat it up with sodium hydroxide. And sure enough, all the metal fluoride gets converted to metal hydroxide. And once you have metal hydroxide, that can easily be redissolved under low pH and regenerate the rare earth ions. And I should point out that if you look at any of the adsorbents, there is no evidence of fluorine present at this stage. So all the fluorine's gone. Now, that doesn't mean that we've necessarily converted all that we adsorb, but there's none left on the carbon after this reaction. So then what you end up with is your carbon regenerated, and you can complete the whole cycle again. And so if you're trying to envision how this would work, you'd probably have to have a couple of beds where you could then adsorb the PFAS, convert it to the metal fluoride, and by the way, the product here is that you're ultimately going to make, sodium. If you take sodium hydroxide and metal fluoride, you make sodium fluoride, which can be used elsewhere. You could even fluoridate water with sodium fluoride. So that's the system that we ultimately came up with. So, and again, this just gives you again a view of what we think is happening with the again. This is using the carbons. So, another thing, and I'll just finish with this, is that we're looking at ways in which we can capture that fluorine and make the whole thing catalytic in the DMF instead of just precipitating metal fluoride. One of the things we're looking at are things that bind fluorine. And here's an example. This is a calixaprol. This ligand is an anion binder, and it changes color. It's colorless without fluorine. You add fluorine, and it changes color. And so if we do this chemistry with a rare earth ion, you will see that you can obviously generate fluoride that binds to the calixaprol. So it may be possible with the right binding agent to do this chemistry and move the fluoride directly. But again, if you think about how much fluorine is in the environment, well, unless we're treating that contaminated soil, that's going to be more concentrated. Just treating water, you'd have to pre-adsorb those PFAS. And here's an example of a rare earth double hydroxide. So the metal hydroxide itself is cationic. Normally, these layered like clay-like materials are anionic, but for these double hydroxide type structures, they're cationic, and so they very effectively adsorb the PFAS. And you can actually see, if you just look at the EDAX of these double hydroxides with the fluorine, you could see that they readily absorb the PFAS. And of course, you can see the layer expansion in these structures. And so this might be a way in which you can combine the adsorption and then ultimately the conversion of the PFAS as well. So those are some of the things that we're also trying to take a look at this point. And one last thing here too. This is actually kind of interesting. So you've got hundreds of PFAS molecules, and here's one here with a hydroxyl group. So this is basically propanol, perfluoropropanol, and or hexafluoropropanol, I should say. And we put this into DMF and water. Now, normally, if you take water and DMF, they're complete, okay? Which is, again, part of the challenge if you're trying to develop a system by which you're going to remove and degrade the PFAS molecules. So, but this is interesting. If you take DMF and water, and then you add the PFAS molecule, it phase separates, okay? And the PFAS molecule actually partitions into the organic phase. So here's the organic phase, here's the water phase down here, and we can verify that the PFAS molecules are in there. Unfortunately, when we take this system and we heat it up with yttrium, we don't see any yttrium fluoride being formed. So it's not, at least up to this point, we haven't been able to remove the fluorines off of this molecule in the system. But it does give you some ideas that gee, maybe there's some interesting ways in which if we have a mixture, we can phase separate them. And if you can then take this solution here and do the chemistry with it, then that might, again, facilitate a process for degrading the PFAS molecules. So kind of interesting. All right. So with that, I'm going to finish up here. And hopefully you can see how we started looking at rare earth ions, metal organic frameworks, and then ultimately ended up with PFAS molecules. And, it's pretty clear that these rare earth ions, the reactivity is there. Appears they do have to be bound to the PFAS molecules. It's very, very solvent dependent, as I pointed out. And though the position of your fluorine seemed to be important, and if you're going to actually make a process out of this, you probably need to have to pre-absorb the PFAS onto something, such as the carbon that I talked about. So, and there's a lot of interesting applications for some of these fluoro-bridged metal organic frameworks that I talked about, not just in the radiotherapy, but in a variety of other applications as well. So with that, I will conclude and be happy to answer your questions.
Thank you. Thank you. Very interesting talk. We have a few minutes for Q&A. And since we have a small group, so if you have any question, you can unmute yourself and we can have an open discussion. So I have a question. So in the cycle, the PFAS removal, you have a carbon absorption and like use the metal framework RE for regeneration. Have you done any like a quantitative analysis, the percentage of the carbon recovery or the percentage of PFAS removal?
Yeah, that's a good question. We know for sure after the reaction with the rare earth ion that there's no PFAS left on the carbon. We know that for sure. What else we might have in solution, that's a good question. And part of the complication there is, even if you still have some fluorine in solution, we don't really know at this point what that is. So, like I said, we've looked at NMR in the past to try to figure out what you have in solution, and it could be metal fluoride. So just at this point, we don't really know what else could be in solution. So it would be great if everything was converted to metal fluoride, but we obviously don't think that's going to be the case. You're still going to have some species in solution that'll have some fluorine on it, and we don't know at this point what that is. Right now, we're trying to, develop some methodologies with NMR and mass spec, but again, we don't have these standards. So trying to figure out what we have, and that's not our expertise, but anybody here that's good at mass spec or NMR, we'd be happy to collaborate. But you're right. You don't really know for sure what you have in solution. Now, when you have something like the 2-fluorobenzoic acid, that's trivial because that's one fluorine, and you know exactly what you have afterward. But for a PFAS molecule, you don't really know. You know.
Yeah, in slides you show that the RE ion can take the fluorine from the PFAS, the structure, those only 2 fluorine elements, which is close to the COH group. Is
Right.
that
So, and that's based on, if you look at fluorine NMR, what we think that position is, that's where most of the fluorine is removed from. The other sites, it does look like some of that's removed, but percentage wise, it's not as great as that 2 position.
okay? And also, you mentioned a couple times that the solvent is very important, right?
Yeah.
So you think that's something related to the solubility or any other special properties?
We think molecules like the dimethylamine is important. And we've tried reactions where we've used a different organic solvent and just added dimethylamine, and we haven't really seen any positive results. So, it's just whatever fortuitous DMA that you generate, by decomposition of the solvent is what we think is doing the chemistry.
So the solvent is not like a performed as a solvent, probably also performed as a reactant.
Yes. Yeah, we believe so. Because if you try to do this reaction in like DMSO, for example, or acetonitrile or some other solvent, it doesn't appear to work. So, but I think we're just scratching the surface here of some of this chemistry. Whether it's the metal organic frameworks or whether it's the types of PFAS molecules or the solvents, I think there's a lot of stuff to do here. So.
Okay, another question you mentioned, like for therapeutic application, you mentioned one slide saying that the thermal stability is important, which is up to 200 degrees C.
Well,
so
yeah, I mean, you can actually add a chemical thermometer in the reactor to figure out what the temperature actually got to, but we know it's over 120 degrees, put it that way. And then if it could go much higher, but then we don't know for sure. So you want something
that specific application, the thermal stability is important, very important, like up to that high temperature.
Yeah, but in actuality, that's not that unusual. I mean, we've got some metal organic frameworks that are stable to 400 degrees. So, yeah, but then there are some that'll fall apart at 100 degrees. But for most of these cluster type MOFs that we've made here, they're all pretty stable. At least 300 degrees. So,
yeah.
Mm-hmm.
Oh, and also there's another question. I think slide number 13, you mentioned using the RE for recovery of rare earths from coal fly ash. Like you use some carbon. Can you?
That's a whole other talk.
Yeah. Okay.
Yeah, we do a lot of stuff with different carbons, and they're some of the ones we make a very high surface area mesoporous carbons that are very selective for these rare earth ions, and we think that has something to do with the formation of these clusters, because you can
you have very high surface area carbon, so made from what's the raw materials what you made?
So it depends, but interestingly enough, we can actually use rare earth ions to make the carbons. And this chemistry in itself is interesting. So you take a rare earth oxide, and by the way, calcium and magnesium work too, and it's the same chemistry. If you take acetylene and you react it onto the metal oxide, you end up making a metal acetylide. Okay. And then if you steam it, it forms carbon. Okay. And this is the same chemistry they used to use in miners' lamps, you know, with the calcium, right? And that's how you ended up with acetylene gas that you could then light and then, you know, use it in a lamp. Same chemistry. So you basically end up making a metal acetylide and it forms a carbon. But the carbons you make are highly graphitic, conductivity is as good as copper. And of course, they can be mesoporous depending upon the starting metal oxide. So if you're using a metal, whether it's a nanotube or just a mesoporous metal oxide, then you can you end up making a templated structure of the carbon, which then has the same structure as your metal oxide. So yeah, a lot of interesting chemistry there.
I guess we have a question from the audience. Shelby, you can unmute yourself and.
Yes. So I guess I was particularly interested in like what you showed about the I guess the way to destroy the PFAS with irradiating it and the photocatalytic. I know that's just one of the ways, but do you know if like anybody has used like plasmonic nanomaterials, or do you need to have those rare earth metals?
Oh, no. The photochemistry has got nothing to do with the rare earth metals. These are, you can use anything that's got a band gap that you can absorb, UV or ideally visible light that would then ultimately generate free radicals, because that's what's going to do most of your chemistry, is generating, hydroxide radicals and things like that. That's where most of your destruction is going to come from. So, maybe, plasmonic materials might work too,
Okay, thank you.
It's always a question though of how do you scale something like that up, and if you're treating a carbon, or you're treating a soil sample, do you get enough light into these samples to be effective at destroying the PFAS? I don't know, but it's certainly, I think that area is still wide open. Lots of different things to try.
Yeah, thank you.
All right, it's 1:03, I guess we stop here. It's a very nice talk, very nice discussion. And thank you everyone for joining us today. Thank you and have a good rest of the day. Thank you.
All righty, and if anyone has any additional questions, feel free to contact me. It's just balkus@utdallas.edu. So
sounds good.
Thank you.
Thank you.
All right.